Today here with me is Simon Knowles. Simon is the co-founder, CTO, and EVP of engineering of Graphcore. Graphcore is a computer processor company based in the UK who have created a completely new processor, the IPU, that is specifically designed for AI compute. We have spoken about data and AI robots who use it to perform actions that help humans in the real world, like doctors or warehouse managers. But something we haven't spoken about yet is just how much compute processing is required to run these. With Graphcore, Simon is helping to push the limits of what's possible with hardware so that new AI companies can actually bring innovations into the real world. He has been designing original processors for over 30 years, and I'm glad to be able to finally speak with him here on the podcast. Welcome, Simon.
Thank you for inviting me onto your podcast.
Well, so glad to have you here. It's been a while since we've seen each other, of course, due to the pandemic. But I do fondly remember us hanging out in New Orleans for the iClear conference now a couple of years ago. That was really nice. And glad to see you again, at least over Zoom now. Now, you're probably the biggest chip expert among my friends. Before we get to your new company, I want to reflect a little bit back in history of when I think about the history of AI. There's been often a lot of promise, and then a lot of excitement, and then often AI winter sets in, and things are a bit calmer, or even disappointment exists, and then things kind of take back off later on, and so forth. Now, arguably, the latest takeoff in AI was sparked by the ImageNet moment in 2012, where Jeff Hinton with his students Alex Krzyzewski and Ilya Sutskever showed that you can train deep neural networks on the ImageNet data set, standard benchmark computer vision that Professor Fei Li at Stanford had put forward, and it just blew everything else out of the water. It was classical computer vision, had like a pretty high error rate, and then this all of a sudden cut it in half, and things just took off from there. And that was 2012, right? And one way to think of it is, of course, it's the reincarnation of neural nets. But then when going a little deeper into it, I think most people would say a big part of it was that at the time, Alex Krzyzewski, the lead author, the student lead author on that work, was somehow able to leverage GPUs rather than CPUs to train the neural networks. And as a consequence, train on a lot more data, a lot more effectively. And so to kind of get going in the direction of AI compute, I'm curious, can you maybe explain, why is a GPU different from a CPU? What's different about it, and why is it better for AI compute?
I suppose if you're not deep in the hardware of building processors, you may not realize this, but there are quite a few different types of microprocessor. Mm-hmm. So the processors that Intel make that we call CPUs, they are designed to be almost a jack of all trades. But there are a whole load of other types of processors. So one example of that is the GPU for graphics, but other examples do exist. So network processors, for example, whose job it is to inspect and modify packets of information passing through communications networks, are profoundly different to GPUs and CPUs. Likewise, signal processors, or DSPs, digital signal processors, they have emerged, and in fact, a number of different types of those have emerged. Their job is to do the maths of communications. And actually, they look quite different inside, again, to a CPU or a graphics processor. Let me give you one other example would be a media processor. I actually built with my team a media processor, one of the first dedicated media processors in ST Microelectronics. Its job was to do encoding and decoding, MPEG signals, JPEG signals, H.264, that sort of thing. Again, profoundly different structure. So in what way do these things have different structure? Well, there are really three sort of main axes of difference between processor classes. One is, how is parallelism expressed?
Mm-hmm.
In other words, how do you try to get more performance by building a machine that does in parallel? The second thing is, what is your memory hierarchy? And that's largely a function of what type of data structure do you need to access and how do you need to access it?
Mm-hmm.
And the third characteristic is, what shape and size is your arithmetic? Because you're going to burn a lot of the power doing arithmetic of one sort. Do the arithmetic numbers need to be integers or floating point? How big do they need to be? AI, great example. Probably the first application for very high performance processing on very low precision numbers. People like to compare AI with traditional high performance computing, HPC, but it's their opposite. So GPUs, what's different about them? Well, on a GPU chip today, you will find quite a lot of independent processors capable of running independent programs.
Mm-hmm.
However, within each of those independent processors, you will also find very fat vector data paths. Typically 1,000 bits wide. GPUs are originally designed to process arrays of pixels, or more primitively, 3D world models being projected onto arrays of pixels. And so you have the sort of parallelism you might expect if that's the task that you need to do. In other words, things are generally 2D or 3D objects in memory. So your memory hierarchy is designed to allow you to fetch those efficiently, and your arithmetic is designed to allow you to process on those efficiently. Now, Graphcore's chip, just to give you a counterexample, a bit different to that. One of our sort of design presumptions is that actually the data structures necessary to do sort of intelligence processing.
Now, these GPUs are different from CPUs, and back in 2012, all of a sudden this breakthrough happens, where thanks to GPUs, it's possible to train neural networks that are much larger than what was possible before, and the results are so much better. In what might seem parallel universe, but definitely is not, I hear you are going to a tavern in Bath, the Marlborough Tavern, back in 2012, same year. Tell me about what happened there.
Well, the Marlborough Tavern moment that you refer to was when Nigel and I met in the Marlborough Tavern in 2012.
Mm-hmm.
We'd had a conversation actually before that. Nigel and I have been friends for many years now, and we were speaking often about what we might do next together. And we had a conversation before that in which we conjectured what would be the best place to try and start a new chip company, the best field. And we actually came up with three. One was using ARM cores to build heavy servers to compete with x86s.
Mm-hmm.
One was the Internet of Things, the famous IoT, super efficient things that would be pervasive in all products. And the third was AI. And we had sort of decided to cogitate these things ourselves. And we came together in that famous 2012 Marlborough Tavern meeting and compared notes. And we were of the same mind. IoT looks rather dull. In fact, the interesting thing about IoT was, what do you do with the data that you've gathered? And the answer, of course, is AI. The second one, that involved trying to walk through the front door of a really powerful incumbent in the shape of Intel. That's hard work for a startup. Eventually, of course, ARM server chips will emerge. They are already emerging. But hard work. Whereas AI, the more we looked at it, the more we thought, this is sufficiently different and has sufficient potential as a market that this could be a real big deal. And that was pre-AlexNet, as I say. So in other words, it wasn't informed by neural networks. Interesting historical footnote to that. I met Jeff Hinton and we discussed neural networks in the mid 1980s.
Oh, wow.
My very first job was in a UK research base with the now rather quaint name of the Royal Signals and Radar Establishment. And we did research, government-funded research into all sorts of things. That establishment was responsible for much of the development of liquid crystal displays, for example. Not well known. However, one of the fields that I was personally involved in was trying to use neural networks to interpret human speech, spotting key phrases and things like that, for security purposes, you can imagine. And neural networks, well, we built one in silicon back then.
Oh, wow.
Toy. We conjectured that if we could build one maybe 100 bigger, then maybe we could do the job we wanted to do. Well, we were probably wrong by a factor of 1,000,000. Now we can do that job, no problem. But 100 times, that was a woeful underestimate. But those of us who are old enough will remember that neural networks tried to break out in the 1980s. I think they were first conjectured in the 60s. They tried to break out in the 80s, but we didn't have the technology to enable it. And then in the 2010s, starting with Alex Krizhevsky's famous paper, they broke out for real because suddenly, or by then, we had the horsepower to make them work.
So it's interesting that you had the tavern moment, and that inside that you see AI as the next big space with demand for compute, effectively for the next generation of compute. And then AlexNet moment happens. I mean, did you call up Nigel or something and say, "Hey, remember our conversation? Now, definitely we got to go for this"? Or how did it impact your thinking when that happened?
No, by then we decided, early 2012, we decided it was going to be AI and we were going to do a chip company. Now, you couldn't have chosen a less fashionable venture investment theme than heavy chips at that time. Uh-huh. So it was clear that we'd have to do it slowly and sort of choose our moment to try and kick it off with venture funding, even though we'd had a couple of successful chip companies behind us. So there were certainly investors who would invest in whatever we chose to do. But actually, I did spend a bit longer sort of researching it and trying to work out what to do. Until about 2014, when we kicked the project off in earnest and started to hire engineers. And we did that. We did that before anyone knew about Graphcore. Graphcore actually didn't become sort of public until 2016.
Right.
We incubated it initially inside another chip company. Now, you might think that's slightly odd. But in fact, that's exactly what we did with Element 14, the first startup. We incubated it inside a computer company called Acorn. So, it was at least a way of getting started that we had done once before. Yes, anyway, so once we started hiring engineers and sort of cranking up the effort, of course, we did become more alert to the rapid pace of CNNs. And adapt our architecture more towards that. So it started to acquire more of the kind of structures that other architectures have acquired. For example, we built a matrix engine into the processors on the device.
Maybe zooming out for a moment, if we think about AI, there's data sets. There's then the training these days of the neural networks on that data. And this can be trained across so many different applications, speech recognition, image recognition, recognition in videos, self-driving cars use AI processing and so forth. And one way to look at it is that there's so many applications, and here you are, it seems, developing a AI chip for all these applications. Am I right? And what is it that makes it possible and important to have a dedicated AI chip compared to past kinds of compute?
I think the honest answer is that nobody knows. If you set out to build a new type of processor, mm-hmm. You really have to have a sort of 20-year perspective. on that, because not only do you have to build the processor, but they're obviously going to have to build programming tools, and people are going to build applications on top of that. And so if it's not going to last 20 years, maybe it's not worth doing. So what you try to do, of course, is to say, well, where are we going to be in 20 years' time? Well, nobody knows, as I say. A few years ago, we didn't know that neural networks would be quite as ubiquitous as they are today. In 5 years' time, we may have discovered something else that isn't neural networks. So a processor designer can't afford to just harden what exists today, or at least shouldn't. There are some examples of startups who have literally tried to do that. There are also some projects like Google's TPU, which do that very knowingly. The Google TPU, as I say, is a rather lightweight processor wrapper around some fixed function hardware. And Google, I'm sure, are doing that because that's what they need today. And if they need something tomorrow, they'll do something different tomorrow. So they're not trying to build something that's quite as long-lived as we are. But from our point of view, we can't afford to harden today's fashion. So what do you harden? What do you focus on? Well, you try and focus on the fundamentals. Massive parallelism, obviously, because everything we know says you need a lot of compute. The only way we can deliver a lot of compute is by having lots of parallel computations going on. We can't make chips just run faster and faster. So that's one thing. Low precision arithmetic. That appears to be fundamental because, I suppose because learning from data is an intrinsically probabilistic task, and probabilities construction are not very precise. So you can imagine having a lot of very imprecise numbers that allow you to do precise things. The structure of the data is interesting, and this is really the reason why Graphcore is called Graphcore. Some data is conveniently structured into vectors or two-dimensional matrices. Some useful data. So vectors occur in sequences, like sequences of word pieces in a sentence. That's quite useful data. And obviously matrices, they occur in pictures, arrays of pixels. So these are natural data forms. They're quite convenient. However, what happens in a neural network? Well, you start off with data that looks like that. And then gradually you transform that representation into some, frankly, unknowable intermediate representation. And then eventually, step by step, through many such transformations, emerge with something that's useful to you, which perhaps is another simple 2D or 3D data structure, and perhaps isn't. It's dealing with concepts. It should have a much more general view of the information that it contains than a set of points in a 2D matrix. The same applies, in fact, not just for the intermediate representations, but even for the input and output representations of some other types. The classic recommender system graph that companies like Amazon are built on is a graph structure. Facebook's friendship structure or relationship structure is a big graph. Molecules are graphs. Nature is full of graphs. And the graph is almost like the mother data structure, isn't it? So our other foundational principle was that you really wanted to be able to handle graphs as data structures generally. Whatever sort of AI you were going to do and however you were going to do it, maybe not on neural networks, but graphs. And what characteristic do graphs have as far as a processor is concerned? Well, they're very high dimensional. Now, what does that mean? Well, it has a massive effect on your memory structure. If you've got, low dimensional, like one dimension, then you've got two neighbors in your sequence. And you can put those two neighbors at adjacent addresses in a memory that you've built and go and fetch them. Now, you can't do that in 1,000 dimensions. So what happens when you embed a high dimensional data structure into the sort of low dimensional memories that we can actually make is that you induce sparsity. You scatter your neighbors to the four winds. So when you want to process on your neighborhood in a graph, which is normally what you want to do, you have to go gather things together. It's a classic sparse problem. So that's the other fundamental that we bet on. We bet that the data structures in the end would need to be graphs of great complexity. I think actually the neural network world that we didn't anticipate being quite so pervasive is now moving in that direction. Graph neural networks, I think, are, I don't know, they may be at their AlexNet moment. To me, we've had two AlexNet moments so far. We've had the AlexNet moment itself, and then we've had the breakout of Transform, almost the second one. And it wasn't really the transformer that was interesting. It was the fact that that structure could harness unsupervised learning. That was the interesting thing.
And under the hood, the transformer is quite different from the previous types of neural networks in that it actually has this, well, the original transformer has a dense graph structure, but it has the graph structure that you're talking about. It sounds like you're building the right thing, even before you discovered how to actually, program something that does something really interesting with it. You're like anticipating this need somehow.
Well, I think so. I'll tell you how I sort of view these interesting different types of neural networks. And this isn't a particularly original view, I don't think. So signal processing emerged to have essentially a kit of key functions that you can just apply in various ways to do all sorts of useful jobs. And those key functions in signal processing are things like finite impulse response filters, infinite impulse response filters, samplers, Fourier transforms, that sort of thing. And we build signal processing structures, such as in your telephone and in the world's communication infrastructure, by composing these sort of basic blocks into all sorts of clever arrangements. I think neural networks are sort of turning out the same way. They're layer-wise because we find that the best way to learn things is incrementally, in other words, by many layered transformations of relatively small effect. And we've discovered that there are different types of layers that are useful. There are layers that have a sort of a local convolutional prior associated with them. They're useful for things like images as properties. There are layers that want to basically be able to pick up information from anywhere in a context. That's the job of the attention layers. There are layers who actually ignore the context dimension completely and just do things like project into a larger dimensional feature space and then contract back out of it again, which appears to be useful for sort of achieving separation of things. So I think these layers are almost like the components that we build DSP systems out of. We're just learning what sort of sets is useful. And in future, once we've got a good set of parts, we'll just bolt them together in various ways. I'm quite fascinated at the moment by the convergence of traditional CNNs and attention type models like transformers. And it's wonderful to see that good results are being achieved in image processing by using a few CNN layers at the front and then a few transformer layers at the back. And that appeals automatically to one sense of what's right.
Now, when I think about you starting Graphcore, and it really resonates to kind of go down to these primitives that constitute the core of AI compute. Did you ever worry about the fact that AI is moving really, really fast? Because you say you need to build something that is valid for 20 years. And it seems like, what people do today compared to 5 years ago, sure, there are close relations, but at the same time, it's moving really, really fast. And was there ever a notion of how to make sure that what you design today in your chip is still relevant, as you said, 20 years from now? How can you have confidence in that?
I honestly think that all interesting spaces move really fast because obviously all of the clever people pile into them if they're really promising. When we did the Element 14 startup and built those DSL modems, as they were called, broadband over copper, that was moving really fast. That was the birth of the internet commerce age. It was a really fundamental, really valuable thing, and everyone could see that. That's what drove the tech bubble of the 2000s. The other thing that you need to do is just, as I've said, focus on fundamentals and not on what is being done today. So, the fundamentals of AI, as I've said, low precision arithmetic, massive parallelism. There's another fundamental which we did factor in, which is nothing to do with AI. It's to do with silicon. So I've had the fantastic career privilege of enjoying much of Moore's law. And if I look at this that we have today, the Colossus Mark II IPU, and compare it with the processor, the first processor was built in about 1990 in that first chip company I mentioned, Inmos. The speed we're running the processor at is about 100 times faster. And the number of transistors we can fit on the chip are about 10,000 times more. So about 1 million times more stuff. It's been fantastic. Unfortunately, it's over. Pretty much. Silicon has a power problem. This is not a surprise. Anyone in silicon will tell you that. Silicon has a power problem. So the other thing, which is fundamental, if you want more and more performance, then you're going to have to focus on more and more power. How's that reflected in our architecture? Well, by making sure that memory structures and processing structures are very close to each other. Most of your power is involved in moving stuff around, not doing maths on it and not just remembering it. So the other sort of foundational principle behind our architecture, the idea of what's called distributed computing. In other words, if you've got a large amount of logic and you can build logic gates with your transistors, you can build memory with your transistors.
When I think about starting a chip company in the AI space, and I think most people, the first thing they'll think is, well, NVIDIA is providing a lot of the compute in the AI space. GPUs are quite popular, and clearly you're going to have to compete with them or carve out a part of the space that they don't manage to get to or something. I'm kind of curious, how do you think about that? How do you see that play out? Because they're a big company, you're the startup. I mean, it's got to be in your mind sometime, like how do we actually, leapfrog them or something like that?
Yes, they're a very dominant force in AI already, and I'm not expecting that to change. I'm not expecting NVIDIA to disappear or be defeated by any new arrival. But what we do expect is that the scope of AI as a concept, in other words, the idea of computers learning from data rather than needing to be told what to do, is sufficiently pervasive that it will touch every aspect of computation and therefore every aspect of human application of technology. In other words, AI is it's pervasive across the whole future of technology. Now, is all of that going to be satisfied by one architecture? I think it's very unlikely. I do think actually that probably quite a rich spectrum of different architectures with different strengths and weaknesses will emerge. Mm-hmm. I always say that if you're a startup, rule one is don't try and produce a better version of what the big incumbents got. Don't try and out-engineer the 600-pound gorilla. You do see a lot of startups trying to do that. To some extent, we tried to do that in our second startup, Icera. We tried to out-engineer Qualcomm. I think we succeeded in out-engineering them because the incumbent has so much market power that a better product that does the same thing isn't enough. What that means inevitably is that for some areas, you won't be as good, but for other areas, you'll be better. So we're not trying to build a better GPU. That's one reason why we've called it a different thing. It has a different shape. It will do different work, but it will do some AI. I think a lot of AI better than GPUs. And also, I'm completely open-minded about there being other viable approaches to deliver value in the age of the AI computer. I think there are some other very promising startups. But I am surprised and a little bit disappointed by how many of the startups have decided just to try and clone a GPU. That makes no sense at all to me.
So I like this notion of this space is growing so quickly into so many directions, and targeting that growth rather than just what is here today and just try to do it a bit better. And you alluded to this notion that there are some places where IPU will be more suitable and maybe other places where a GPU might be more suitable. Is that kind of a vision of the future, or would you say it's already the case today that there are certain workloads where it's clear IPUs would have the edge? And can you say a bit more about that?
I think it's becoming clear already. The simplest way to think of it is that GPU's got lots of processors on the die. So if you have a sort of arbitrarily structured data structure, we have a larger number of processors that can go off to bits of that data structure and do useful work. Effectively, independent of the homogeneity of the data structure. If you have more processors, you can do more work. And we certainly have demonstrated that in places where there is some element of sparsity, whether it's conditional execution of code or conditional access of weight sets or just perforated data structures, that do particularly well. The other advantage that I think we have now demonstrated against GPUs is an energy efficiency advantage. So our chip is about 50% memory, 50% logic, and they are intimately intermingled. So data values don't usually have to move very far to be processed. And that's quite different to a traditional processor, even a highly parallel one like a GPU. And if you look, for example, at the performance that you can achieve on standard benchmarks today, like natural language processing, transformer type models. If you look at the performance per watt today, in other words, you take a budget of 10 kilowatts or something like that for your computer rack, we can get more performance out of IPUs than can be got out of GPUs because of that energy efficiency. And that's with chips which have more or less the same sort of peak number of arithmetic operations per second as each other.
So if we can make this a bit more concrete, maybe you said sparse compute, right? And of course, as a company, Graphcore, you build a general engine that anyone, including us, at Berkeley, we've worked with Graphcore IPUs and so forth. Anybody can build things on top of, right? But can you give some examples of maybe specific applications that maybe when we just see the application, we might not know, but under the hood, it relies on more sparse compute and hence has been a very natural fit for the IPU? Well,
so the most obvious example of sparse data structures that are useful is molecules. Molecules very rarely arrange themselves into convenient lines or squares. They obviously are graphs, almost axiomatically. It's also the case that useful molecules are often not very big. They can have terrific complexity of behavior and still be quite small. A molecule of a few thousand atoms is still a molecule of fabulous complexity. So if your job, for example, is to try and take a molecule of a certain structure and predict its properties, or to take a set of properties and try and work out what structure would express those properties, that's a great example. It has two fantastic properties that make it suitable for an IPU. The first is small enough data structure that actually the whole thing can live in the memory that's on our chip. And we have terabytes per second of access bandwidth to that memory. So that's really special memory. And then the second thing is, because of our massively parallel structure, we can operate on that irregular data structure far faster than other architectures. So that's the best example I can give you. Working on molecules. And how many applications are there for that? Well, crikey, a great many. The discovery of new chemicals, better materials for fixing diseases, for coronavirus, etc. Even just understanding how these molecules behave is a fabulous potential benefit to society. Other examples, well, we've had quite a lot of traction in the finance space. A lot of finance models turn out to be abstractly structured and also kind of probabilistic rollouts of what might happen next. That requires the ability to generate a lot of random numbers, and our machine has powerful random number generators on every one of its 1,500 processor cores. So it can, if you like, it's the world's noisiest chip. We can generate more noise per second than anyone else by quite a lot. But even if you go to simpler stuff, we talked about transformers and natural language processing. We can outperform GPUs in that space as well, and that's just processing sequences. So even in that space, actually, there is a demonstrable advantage. So even if you take things that are not graph structured or obviously sparse, like natural language processing, it's just processing of sequences of word pieces, we can outperform in that space as well, outperform GPUs. And that's just the advantage of being able to design with a clean sheet of paper. One of the advantages a startup always has. Having sold Icera to NVIDIA, of course, we know quite a lot of the engineers in NVIDIA. We know Jensen Huang quite well, and have enormous respect for those people. I think they've done a fantastic job of moving their GPU, their graphics processor, into the AI space and serving the community as a result. But do have that disadvantage. It is still something derived from a graphics processor. If they had been able to start with a clean sheet of paper, I'm sure that they could have built something like ours as well. But you never have that opportunity in a big company. There's always momentum from your previous business.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts.
So Graphcore's technology does assume a certain scale of computing. It doesn't assume that you're going to have a rack full of chips, but it does assume at least that the chip will be a certain size. And the reason for that is we derive great strength from being able to put enough memory on the chip. Now, if the chip's too small, or indeed if the power budget's too small, it doesn't really make sense. So you won't find Graphcore chips in your mobile phone. Our range of interest is from the infrastructure, the cloud infrastructure, the enterprise infrastructure, through to what I would call the heavy edge. Devices with power budgets of a few tens of watts, such as smart cameras. You've probably come across this idea of intelligent retail, where you walk into a shop and all of the AI artillery in the shop works out who you are, correlates that with your account, hopefully, works out what you've taken out of the shop and charges your bank account. That's the heavy edge. In other words, there's quite a lot of processing involved there, and there's a power budget that's compatible with our approach. But I wouldn't say we go down as far as the sort of sub-watt mobile phone space. I think that's for others.
Now, as we're on the topic of other efforts, I'm curious to get your take on, there's this one effort that often comes back in conversations I'm in, which is I'm sure you're familiar with this Cerebras effort, which says we're going to build as big a chip as possible, which seems a bit complementary to what you're doing. And I'm kind of curious how you see the trade-offs between this notion of building, I think, a full wafer chip, which is unusual. I would imagine, at least it's very unusual, versus the more standard approach.
Actually, back in the when was it? The very late 80s, 90s. There was some attempts to use whole silicon wafers, what was then called WSI, wafer scale integration, in particular to deliver memory, but actually there were also some efforts in processing. So what Cerebras have done, I'm not quite sure whether I'm pronouncing that correctly, but stick with it, is really, really impressive, and I wish them all the best. They've basically said, okay, suppose we make chips in the normal way, but then instead of sawing those chips up, packaging them, and then remounting them onto a board, we just leave them on the wafer. Now, the downside of doing that is that some of those chips aren't going to work because manufacturing isn't perfect. So you've got to have enough sort of spares and to work around the ones that aren't going to work. There's also the downside that you have packed all of your processing, and it's a lot of processing, into a smallest possible space, which means you've got the biggest possible power delivery and heat extraction problem. And they're the bits where they've done, I think, really impressive work. Getting enough amps in and getting enough heat out is very impressive. But what's the advantage is that you can use wires made by silicon processing techniques to connect those chips together, very much finer than you would fit on a circuit board. Now, I don't think that advantage is enough. It actually is also a slight disadvantage in that I can't get to the wires that are sort of in the middle of the array. I can only get to the edges. And that means, for example, if I want to attach more memory to the system, I can only attach it around the edges. But nevertheless, it's a really interesting take. I wouldn't say it's a chip. I mean, if you look at the way in which it's built, the chip is actually about 5.5 square centimeters. There are a lot of them on a wafer. That stuff's all very conventional. They've decided not to saw it up, and they've decided to put some more wires over the top that connect those chips together. But it's definitely a wafer. And I think as an engineer, as a chip designer, a processor designer specifically, I think probably the disadvantages of that assembly outweigh the advantages. But nevertheless, I wish them well. I think it's a very bold endeavor, and I, as an engineer, I hope it works.
Talking about some of the challenges in bringing chips into existence, right? I think the most common thing when having the past talk with friends about, okay, well, how about, what would it take to design a chip for this or that? It's like, well, going from designing a chip to actually taping it out and having it actually work is a really long path and very difficult. Can you say a little bit about the Graphcore journey from, starting when you started on designing the first Graphcore chips to getting that first one taped out, and what happened in that process?
The Graphcore's current chip, the Colossus Mark II, is the most complex chip that's ever been made, as measured by a number of transistors. And we have the most transistors that anyone's ever crammed into 8 square centimeters. Now, if that had been our first attempt, I'm sure we would have failed. The reason why we've managed to do this is because the core of the team have been together for a very long time doing this sort of thing. In fact, the core of the team is much, much older than Graphcore. It goes back through both of the previous startups. In fact, we even have, I think, 5 or 6 people who go back 30 years to the processor team in Inmos, who have been building these things. We have taped out a custom designed processor in every process node since about, to TSMC, in fact, in Europe, in every process node since 150 nanometers. So 150, 130, 90, 65, 40, 28, 16, and 7. 8 consecutive process nodes. We probably didn't beat the Californians, I have to admit, but the first in Europe. And every single one of those has worked straight out of the box.
Wow.
So this is a team that knows its onions, as we say in England. Built it, and obviously there's huge complexity in doing that. You can't really learn at university. So we had the pleasure of learning it in a large semiconductor company and building on what we learned from that point onwards. Building chips, I liken it to building aeroplanes, passenger aeroplanes. Mm-hmm. What does it take to build a jumbo jet? Well, it takes such a diversity of skills and such, complexities involved that there's no way, for example, if a bunch of really smart new PhD students $1 billion and said, go and build a passenger jet, that they would be likely to succeed. You probably need people who've done other things like that before. We happen to have such a team. The reason why this is interesting is because aren't that many teams in the world available with that sort of skill set? And yet there are now a lot of people in the world trying to build that sort of chip. Mm-hmm. And I do find that a little bit distressing because I think it means quite a lot of ventures are not going to succeed, which is never good to see. A lot of the cloud compute companies have decided to follow Google and have a go at making their own chips. Mm-hmm. People ask me whether they are competitors. Well, in a sense, an in-house team is a competitor because it means they might not buy our stuff. Mm-hmm. I think the sad truth is a lot of those companies won't succeed in putting together a team that can deliver that sort of device. And when that happens, they will look elsewhere to specialist chip companies like us to fill in the gap.
I really like this notion that you need a team, a pretty large expert team with many strengths. Different people bring different strengths. I would say that that's a little different from a lot of other AI efforts where often, think about the Jeff Hinton, Alex Yashesky, Ilya Sutskever breakthrough, the 2012 AlexNet moment. That was 3 people, right? Of course, building on other people's work in the past and their own work in the past, but that was ultimately 3 people doing that breakthrough, right? Mm-hmm. It sounds like in chip design that it's not going to be 3 people doing a functioning chip.
It's interesting. It doesn't take an enormous number of people. I rail against people who have said in the past, chip design is getting exponentially more difficult. Chip teams are getting exponentially bigger, etc. That's basically not true. The size of team that it takes to build a state-of-the-art microprocessor like our device, we produced our first device with a team of about 30 chip designers and a similar number of software engineers writing tools to program the device. 30 years ago, we would have built a system of state-of-the-art complexity with the same number of people. So just to add some more numbers, it took us about 3.5 years to develop from sort of first ideas, architectural ideas, to our first generation chip. We've now done the second chip. That took about another 1.5 years after that. It took us about 100 man years to do the first one, I suppose, or 100 person years. And I would say that's what a startup can do. Roughly speaking, yes. If you want to build a competitive new chip and spend 100 million doing the first one, and you might spend 500 million building your business. So it's not for the faint of heart, investment-wise.
Now,
just to make sure you've got people who can pull it off.
Now, if you work with such a, I would say, not a massive team, but a team with complementary expertise, you said you need maybe about 30 on the hardware side, 30 on the software side, but very complementary expertise even within hardware, within software. Gotta imagine, the collaboration mode must have changed in the last year with the pandemic. What were some things you did to make sure the teams could keep collaborating very closely?
Actually, for the team that we've already, we went into the pandemic with 430 people, I think.
Oh, wow.
And for that team, it's already very well knit. And the pandemic just meant, obviously, a lot more time in Zoom calls with each other. We discovered, for example, that meetings are really very efficient if everyone's on Zoom. So actually, that might stick as a modality. You do miss the more spontaneous stuff. But I think our team was sufficiently close-knit at that scale that I would say our productivity probably didn't drop over the last year. The bit we found really difficult was integrating new people. So we were very fortunate we were able to continue to grow. We raised more venture investment to fuel that. So we have been recruiting. There's a special chemistry that comes from being with people. And you need a lot more of that chemistry in the early stages of forming a team relationship. So we're very much looking forward to getting back to the office. I think our work patterns will have changed forever. I suspect that many people will be sort of partially in the office and partially remote, ongoing. However, we're all looking forward to being together again.
Now, when I think about the AI chips today, right, and I imagine you'll agree with me, but I'm curious. There's still a big gap between the chips designed today and the human brain. And I'm not talking about the software. Of course, the human brain runs a more interesting kind of software and so forth, but just the hardware. For example, if you just look up average human brain uses about 20 watts, which, that's a very low power budget compared to current chips, even the world's best chips, right? Can you say a little about the gap between human brain and current chips, and how it might be bridged or maybe will not be bridged? What's your thinking in that regard?
There is, of course, a school of thought which says that we should build silicon processors that have very similar structure to biological neural systems. I don't really buy into that, because I think that there are huge differences in the physics of electronics, and those differences in the substrate probably mandate a different approach to producing a computing fabric. Obviously, it's fascinating to study the brain, to try and work out how it does computing, and I don't doubt that we learn a lot by doing that we might apply to future computers, but I don't ultimately see any reason why a silicon computer would have the same morphology as a wetware computer. So I'm not an advocate of neuromorphics, as it's called. Now, in terms of efficiency, there is a sort of efficiency limit for computing in any computing structure which does not execute a program reversibly. That's a slightly academic aspect. But there is a fundamental noise-based limit to how power efficient computing can be. And in fact, before we even get to that fundamental limit, there's a sort of practical limit. The practical limit is best understood in this way. Suppose you want to send a bit of information along a wire to some distant part, it's maybe a millimeter away. In principle, you only need to send one electron down your wire. You want to send several thousand electrons. These effects don't corrupt your signal. Now, how far away is that from where we are today is a very interesting question. It's about a couple of orders of magnitude, at least at room temperature. If we're prepared to cool things down, then everything gets less noisy and we can make do with fewer electrons. But about a couple of orders of magnitude. Now, the brain is more than 2 orders of magnitude more efficient than our electronic chips. So there's something more going on there. I would say that it's not fully understood. The fibers, the axons in your brain, I think more understandable. They do carry electrons. It's a charge-based signaling system, just like semiconductors in silicon. And so we understand those. What we understand far less well, though, is the computational functions going on in the neuron cells themselves. And that appears to involve molecular interactions which are more efficient than the sort of charge-based electronics that we're used to. So something different may emerge that augments silicon electronics that allows us to get closer to a brain, but silicon will never get to the power efficiency of a brain for fundamental reasons. It also has one other rather massive problem today, and that is your brain's probably got 100 terabytes of state. That's the weights of your neural network. You've got about 200 trillion synapses I'm not a biologist, but I'm told you have about 200 trillion synapses. And there's been some fascinating research on how many bits of information can be stored in a synapse. Appears to be 4 or 5 bits. Now, we can build a computer with 100 terabytes of state. In fact, I could fit 100 terabytes in a matchbox. Mm-hmm. But unfortunately, if I want to access it as fast as you access the state in your brain, it'll burn an enormous amount of power. And I certainly can't fit 100 terabytes on a chip and do anything useful with it for 20 watts.
That's so interesting. Now, if I think back to my, basic level physics and chemistry classes, electrons are smaller, are only part of an atom. And multiple atoms together constitute molecules. And so when I hear you say that molecular computing in the brain somehow managed to be more efficient than sending electrons around, some of that is a bit counterintuitive to me because the electrons are smaller. Can you say a bit more about why that should not be counterintuitive?
I honestly wish I could. I think it's a mystery to humanity at the moment as to how the brain manages to be quite so energy efficient. But it's not the signaling. We understand that. The signaling's super clever, by the way, in terms of its energy management. You don't just have one type of axon in your head. You have all sorts of different types. Evolution has done a pretty good job of trying to optimize your brain to increase its capacity whilst also keeping a lid on its energy consumption. But the stuff going on inside the neuron cells, well, the more we look at it, I think the more we realize it's quite complicated.
The other number that really stood out to me that you just mentioned is 100 terabytes of information stored in our brain. And indeed, my MacBook Pro has 2 terabytes, which is a little less than 100 terabytes, but storing 100 terabytes on a computer is not too hard these days if you get a slightly bigger computer. And that, of course, brings to the imagination all these things where people upload their brain onto a computer. Not clear how to do that, but storage-wise, it seems like storing wouldn't be the issue. Is the somehow collecting the information would be the
yes, absolutely the case. In fact, Samsung have succeeded. They're sort of experts in memory, but they've succeeded in packing a terabyte into just silicon chip that's less than a square centimeter. It's absolutely amazing. No, the issue with capacity is again one of total computation required. So take language models as we or just transformer structures, say, as we understand them today. We have some examples of fairly big ones. We have things like GPT-3, 175 billion parameters, and training it about 300 zettaflops. Mm-hmm. Today, just to calibrate, the zettaflop is about $1,000 of ownership of computer. In other words, if you want to build a big computer infrastructure, then it'll cost you, if you run it all the time, it'll cost you about $1,000 per zettaflop or $1 per exaflop. That's what's achievable. If you go and rent one from Amazon, they'll charge you about 4 times that amount. But you could build one today for $1 per exaflop. Now, if I take that model and I say, okay, what happens if I scale it to brain size? About a factor of 1,000. Well, the model gets 1,000 times bigger. Okay, so the amount of energy required to train the model goes up by 1,000. But also, actually, the whole point of increasing the capacity of the model is to allow it to absorb more data. So the training data set also gets bigger. And there's been some fabulous work by OpenAI and others on how these things scale. Mm-hmm. And if you apply those sorts of general scaling laws, as far as we understand it, you end up requiring something like 5,000 yottaflops. 5,000 yottaflops today, that's $5 billion to run the program once. And I forget how many years of sort of 500 gigawatt nuclear power station, but these numbers are just out of the question to reach what we might regard as human scale. So what's the answer? Well, clearly the answer is we have to make sure that for every datum we from or do inference on, it doesn't have to interact with every parameter in the system. In other words, sparsity. Sparsity is fundamentally necessary to keep a lid on things. Either that or the neural network paradigm will never get to that scale. But if neural networks are a general computing fabric, as we hope, then whatever their structure, massive sparsity must come. Personally, I mean, there are many forms of sparsity. Personally, I think the most promising and the one that might represent the next of those magical GPT breakout events is this idea of the gated computation. So things like switch transformers and sparsely gated mixture of experts, where token by token, as these tokens pass through layers of the neural network, they select a set of weight state from a very large amount. And that form of sparsity has already been shown to be very effective, even at sort of very high sparsity, very large structures. So maybe that's it. But some form of sparsity is absolutely inevitable if the neural network is ever going to reach human type potential, capacity. And some applications of AI are only useful when we have AIs that have superhuman capacity. So any form of advisor. Suppose you were to interact with an AI doctor. Well, you wouldn't pay any attention to it if you didn't think it was smarter than a human doctor.
Right. Or complementary.
Or a financial advisor. Our minimum standard for listening to AIs is that they're smarter than people. Likewise, if we want an automatic driver of a car to be better than driver of a car, then it'll have nothing to do with, learning the dynamics of a car. It's how other humans are going to behave.
As we think about AI compute becoming more and more sparse to be able to scale up and handle bigger and bigger applications, I'm kind of curious, what's your more general vision for the future of AI? Where do you see it go in the next 5, 10, 20 years, and the role of AI compute in that, of course?
It's very hard to imagine any aspect of computation which doesn't have value added to it by allowing the computer to participate in the job of solving the problem. If you consider a program to be just a capture of a problem-solving method, you could say that all computers so far have not solved problems. We tend to think of them as solving problems, but they haven't fundamentally solved problems. We've had to work out how to solve the problem, codify that method as a program, and then obviously the computer can do it much faster than us thereafter and can do it on an enormous body of data, but it hasn't participated in solving problems. So with the ability of computers to work out their own algorithms, of course, we get over that hurdle. Also, some things that we know are doable because we can do them, such as translating from English to Russian, we can't write programs for. We know they're doable. The classic "recognize your mother" in a set of pictures. We can all do it. None of us can write a program for it. So there are a whole load of sort of tasks that will be enabled, which we can do, but we could reasonably imagine that machines could do better, or at least more tirelessly, or for better economics, or all that sort of reason. I think, AI, the breakout of information technology, you might regard that as the sort of second industrial age. It's going to fundamentally change the way that people live, and I hope mostly for the better. It's easy to forget that you only got to go back 250 years, and if you wanted any work done, the only way of getting it done was human muscles, or if you were lucky, you'd be able to harness an animal to use the animal muscles. And then along came the steam engine, and it meant that we could organize effort, work in that sense. And the people who invented steam engines, well, they couldn't really imagine everyone driving around in a motor car. or you jumping into an aeroplane to go to the other side of the world to sit on a beach for a holiday. I mean, you'd have to be very imaginative to have seen that coming. So likewise with AI, if we build things that are clearly far smarter than people, what happens next? Well, I have no idea.
Yeah, who knows what will be next? I like the way you phrase that, Simon. And the future is very hard to predict, and I'm personally very excited to see what's going to come next. Thank you so much for joining us. I learned so much. Had so much fun catching up with you. Thanks so much.
Thank you, Pieter. It's been a pleasure. What a great time to be an engineer or a scientist.